The universe is beautiful. Thousands of eyes look into the sky every night to catch a glimpse of wonders that it paints with light. But this light does more than create amazing distance. It can tell about the nature of our universe. Using the process of spectroscopy, in which the colors mixed in the beam of light are separated and analyzed, astronomers can uncover the secrets of the myriad sources of light that their telescopes can capture. Without the subtle data carried by the light, our understanding of the universe would be limited to only the beautiful images it creates. Spectroscopy, rather, is the most fascinating part of modern astronomy because it enables you to tell some things about the nature of the objects in the universe in much details without going there and touching them. Okay? Because with spectroscopy, you can tell how hot the star is, how big it is, what mass it has, what the chemical composition is, and you can even tell how far it is away from us. And all the information comes from spectral lines in the spectrum of stars. Deciphering the mysteries of the universe with spectroscopy requires a basic knowledge of how light is created and how it interacts with different types of matter to generate unique spectra. Light exhibits certain behaviors that are important to the design of telescopes and other instruments. Reflection and refraction of light are the basic properties that make possible all optical instruments. Okay. Such instruments are generally combinations of glass lenses, which bend according to the principle of refraction, and the curved mirrors, which depend on the properties of reflection. Okay. In 1672, Sir Isaac Newton described an experiment in which he permitted sunlight to pass through a small hole and then through a prism. Newton found out that sunlight, which looked white to us, is actually made up of a mixture of all the colors of the rainbow. Okay. Light is separated into different colors with a prism. A prism is a piece of glass in the shape of a triangle with refracting surfaces. The bending of the beam depends on the wavelength of the light. As you can see, the violet light is bent more than the red. Okay, this phenomenon is called dispersion. Upon leaving the opposite face of the prism, the light is bent again and further dispersed. Because this array of colors is a spectrum of light, the instrument used to disperse the light and form the spectrum is called a spectrometer. In 1802, however, William Wollaston built an improved spectrometer that included a lens to focus a sense spectrum on a screen. With this device, Wollaston saw that the colors were not spread out uniformly, but instead, some ranges of color were missing, appearing as dark bands in the solar spectrum. Then in 1815, a German physicist, Joseph Fraunhofer, upon a more careful examination of the solar spectrum, found about 600 such dark lines. Later, researchers found that similar dark lines could be produced in the spectra of the artificial light sources. Gases turned out not to be transparent at all colors. They were quite opaque at a few sharply defined wavelengths. All gases did this, but each different element observed a different set of colors and thus showed different dark lines. Okay. Sweet for When the gas were heated, a spectrometer revealed no continuous spectrum but several separate white lines or bright lines. Okay, example of this. Okay, when the gas was pure hydrogen, it would emit one pattern of colors. Then, when it was pure sodium, it would emit a different pattern. Then the mixture of hydrogen and sodium emitted of both sets of spectral lines. From such experiments, scientists began to see that different substances showed distinctive spectral signatures by which their presence could be detected. In these experiments, there were three different types of spectra. A continuous spectrum, formed when a solid or very dense gas gives off radiation, is an array of all wavelengths or colors of the rainbow. Then next is a continuous spectrum can serve as a backdrop from which the atoms of much less dense gas can absorb light. Then, a dark line or the absorption spectrum consists of a series or pattern of the dark line's missing colors superimposed upon the continuous spectrum of a dark line's sources. Then the bright line, which is the emission spectrum, appears as a pattern or series of bright lines. It consists of light in which only certain discrete wavelengths are present.